This is the Introduction to Relativity, Part 3. In the last part, Part 2, we described why it was that Einstein believed it was necessary to take a fresh look at the physics involved in changing perspective from one reference frame to another. In this part, we'll look at the two fundamental postulates that Einstein used in that process. So the postulates of special relativity. So first, it's probably worth recalling exactly what a postulate is. You probably saw that word in a geometry class. A postulate is something fundamental. It's something so fundamental that you can't even prove it's true. You just have to assume it's true at the very beginning before you can build on it to get any new idea. So when you think back to geometry, you had things like a transitive axiom. That would be a postulate. That was where you said if A equals B and B equals C, then A equals C. It seems so obvious, it just must be true, and yet it's so obvious that you can't actually prove it. You just have to assume that it is true. It just makes perfect sense. And so that's what Einstein did, is he thought, well, I've got some contradictions in how it was we moved from one reference frame to another. For example, how we try and add velocities. If you had that car moving to the road, and you also had light moving at some speed relative to the car, you couldn't just add them. If that was failing, then he said, let's go back to the simplest possible things we can trust. And so that's what we're going to do now, is look at the two postulates that Einstein used. The first one takes a few words to explain. It says that the laws of physics are the same in all reference frames that move at constant velocity relative to each other. So that's a lot of words, but I think we'll unpack it and figure out exactly what it means. And I think you'll find it makes a lot of sense. So before we get too far, we need to take a close look at what we mean by this idea of reference frames. That's a really key thing throughout our discussion of relativity. Let me change that back. I want to go to pencil, and now, can I do this one in red, maybe? I can't. Well, I want to underline this idea of reference frames here, because that's really what we care about. Okay, so what do we mean by a reference frame? Well, you probably have some idea about what it might mean. Consider for a minute yourself sitting wherever you're sitting right now, and think about somebody else who's maybe sitting across the room from you. Ask yourself this: are you in the same reference frame as that other person? Or are you in a different reference frame from the other person? What do you think? You might conclude that, well, you're in a different reference frame. You're on different sides of the room, so maybe you have a different viewpoint, a different perspective. If you're both looking at the same object in the room, you might be looking at different sides of it. One person sees the left side of that table, and the other person sees the right side of the table. You might say, well, we're at different distances from things, and consequently that would make it a different reference frame. But in fact, if you're sitting down and somebody else is sitting down in the same room, you're actually both in the same reference frame. And so we need to define exactly what it is that we mean by reference frames. So let's take a closer look at what Einstein meant and what we always mean in physics when we're talking about reference frames. So by reference frames, we'll say that two people are in the same reference frame if they're not moving relative to each other. Okay, that's what we'll kind of use as our definition of reference frames. So if people are moving compared to each other, then they're in different reference frames. If they're at rest compared to each other, they're not moving compared to each other, then they're in the same reference frame. So there's our definition of reference frame. Okay. So now let's see if we can understand what this first postulate of relativity really means. The laws of physics are the same in all reference frames that move at constant velocity relative to each other. Well, let's take an example. Suppose that you're in an airplane and we'll look at a simple law of physics. It's a full airplane, and so of course you have no place to put your extra equipment. Maybe you're flying out to that big bowling tournament in Boise, Idaho, and you've got your bowling ball and you have to put it somewhere, and so you just set it down in the aisleway between the chairs. And if it's a nice smooth flight and the plane's level, it's not tilted up or tilted down, and you set that bowling ball down in the alleyway, in the aisleway there, what's it do? Well, it sits there. That's Newton's first law. An object at rest stays at rest. So you set the ball down and it stays there and obeys Newton's first law. Well, think about it. You're moving hundreds of miles an hour compared to the surface of the Earth, where that same law of physics also holds true, that bowling ball, if you sit it on a flat surface, will just sit there. So that is a case where the laws of physics are the same in two reference frames that are moving at constant velocity compared to each other. And also think about how different it would be if the airplane weren't moving at constant velocity compared to Earth. Suppose the airplane's accelerating, like when you're on the runway. Put that bowling ball down in the aisleway and the airplane starts accelerating forwards, and what's the ball do? Well, it starts rolling backwards. It actually starts accelerating backwards. And that is not first law. According to Newton's first law, the law of inertia, that ball that you set down at rest should remain at rest. It shouldn't start accelerating backwards. So we see these two things. The laws of physics are the same in reference frames that move at constant velocity relative to each other. And we see that the laws of physics are not the same in reference frames which are accelerating relative to each other. So that's what the first postulate describes for us. That's what it summarizes. I think that's a postulate which probably makes a lot of sense. Again, you don't have to go through special training to be on an airplane and moving, hundreds of miles an hour. If you want to pour a cup of tea on an airplane, the tea as it pours out of your cup or out of the pitcher into the cup, it still follows the same trajectory. It doesn't do loop-de-loops or do anything funny, right? So we're used to. In fact, you could ask yourself this question while you're sitting there listening to this or watching this video: how fast are you moving right now? Are you at rest? And of course, the answer depends. You could say, well, you're moving 1,000 miles an hour to the east as the Earth rotates. And yet the laws of physics there would be exactly the same as if you weren't moving. And this law of inertia is one that people commonly use. And so let me mention that as well, that often we refer to what's called an inertial reference frame. And an inertial reference frame is just one where the law of inertia works. And so that's a common way of testing whether you're in an accelerating frame or not, right? So an inertial reference frame is a non-accelerating frame. So you'll sometimes hear that term. Okay, so we've got examples of what we mean by laws of physics being the same in all reference frames that move at constant velocity compared to each other. Now, that last example I used where I asked you, are you moving or not right now, brings up an important point. The fact that since, you feel like you're not moving at all, and yet you could say that you're moving 1,000 miles an hour east because of the Earth's rotation, or that you're moving 18,000 miles an hour east due to the Earth's velocity around the sun. The fact that you can't tell whether you're at rest or moving at an extreme but constant velocity tells us that, well, if you cannot distinguish between those, if no law of physics is different, maybe there's really no difference between. In fact, maybe there's no such thing as really moving or really at rest. And this gives us another way of stating this first postulate of relativity. So a different statement for it. Or you could, if you wanted, you could call it a corollary. Is you could say that there's no such thing as really at rest and really moving at constant velocity. Because if there's no physical law that's different, that means you're not going to feel anything different if you're moving at constant velocity compared to being at rest. And so the whole concept really doesn't have any validity, doesn't have any use. You may have had situations like that where you weren't sure if you were moving. For example, I know I've been in a car sometimes at a stoplight and another car pulls up beside me. And I'm just kind of aware of that other car in my peripheral vision. And suddenly I feel that my car is rolling backwards. And if I'm driving, I might hit the brake to make sure that my car is not actually accidentally rolling backwards. And then I realize it wasn't my car going backwards at all. It was actually the car next to me going forwards. And so I couldn't tell whether I was really rolling at some velocity backwards or whether I was really sitting still. And the only thing I could detect was that relative motion between the other car and me. And that's what we're saying in relativity, is that's the only thing which has meaning, is you can talk about how fast you're moving compared to some other object, but you can't talk about how fast you're moving, period. There's not any absolute reference frame to compare to, no actual rest frame to compare to. So that's the first postulate of relativity. The second one, luckily, is a lot simpler to state. And that is that the speed of light is a constant in all reference frames. So whether the source is moving towards you or away from you, or whether the receiver of the light is moving towards the source or away from the source, it doesn't matter. Whenever you measure the speed of light, you're going to get the same speed, 300 million meters per second. And of course, this is simple to state postulate. This is exactly what Einstein was getting from the experiments that were taking place. He was looking at people measuring the speed of light, and they were finding no difference in the speed depending upon whether the source was moving compared to the receiver of the light. And so he said, let's just make that a postulate. It seems to be a law of physics. It comes right from Maxwell's equations. We'll just take it as truth. We'll assume it to be true and go from there. Now, one thing you have to be careful about this is, as we start studying relativity some more, we're going to come up with some things which seem very strange. We'll learn soon that time runs at a different rate depending upon how fast you're moving. And we'll learn that the length of an object is not a constant thing, but actually as objects move closer to the speed of light, their lengths are actually shorter, substantially shorter than if they're at rest. And these are really hard to accept. It's very weird physics. So what you'll want to do as you encounter these things is to come back to these two postulates and remember which of these two is the weird postulate, which is the strange one. So you might think about that right now. Which of those two things, these two postulates here, is the one which is very strange? And as you think about it, I think you may realize it's really not that first one. It took a lot of words, and maybe you wouldn't have thought of that first one, but it's something that happens all the time. Again, you're used to moving in a constant speed at a car, and you can take something in your hand and just throw it up, and it falls right back down exactly as if you weren't moved at all. That's the one which is actually really normal. It's that second one which violates that addition of velocities that we learned about earlier this year, that the speed of the car plus the speed of the lights coming out of the car should add up. That's what we thought should happen, and yet that's not what happens. So it's that second postulate which is really the weird one, and which is kind of causing all the trouble, if you will. Okay, so that's the end of this part. In the next part, part 4, we'll actually begin exploring some of these strange results that come from applying these two postulates.